Hello. Today we are going to solve one interesting problem named Bertown roads. This is a question of type DFS and finding bridge problem. So it is related to the concept of the finding the bridges in the graph. So first we have to learn how to find bridges in the graph. After that only we will be able to solve this problem. So first let's go and discuss how to find the bridges, and finding bridges concept will be divided into two videos for making it smaller, otherwise it will be a lengthy video. So let's go to that part of how to find the bridges, whether they exist in any graph or not. So come here. First we will be what the bridges means we will be discussing. So bridges means whenever any edges you remove and number of connected component gets increased after removing that edge, then that will be the bridge of that graph. So suppose in this case, if we remove this edge, then the number of connected component will increase from 1 to 2. So the number of connected component get increased from 1 to 2, or either you remove this edge, then also the number of connected components will increase. So in this graph there are two bridges. The first one is this bridge and the second one is this bridge. So how we are going to find these bridges? For that we have to first learn what the DFS tree is. So let's discuss the DFS tree. What the DFS tree is. DFS tree. Suppose this is our root node and we call this root node from the main function. Then how the DFS works? It will see in the adjacency list of this current node. So if it is node visited, then it will come here and it will make a DFS call from here. So let's suppose it has come here and it has making a DFS call from here. After that, suppose it comes here. Suppose it comes here and this node comes here. Now when it comes to this node, since all the nodes connected to this node is visited, so it will trace back. Tracing back, it will come to this node. All the nodes connected to this node also visited, so it will trace back to this node. All the nodes connected to this node are also visited, so it will trace back to this node. Now it will come here. It will make a DFS call from here and check the adjacency list connected to this node. It will come here, suppose. Check its child. If it is not visited, then it will visit. Now since there is no any nodes connected from this node, so it will trace back. It will check here. There is one node which is not visited. It will call a DFS call from here. After that it will check the adjacency list of this node. This node is already visited, so it will do nothing. It will call a DFS call here since this node is not visited. Now in this node there is no any node connected to this node, so it will trace back, trace back, trace back. Now this is the node which is not visited, so it will visit that node. Now traversing the adjacency list of this node, it will visit this node. Now in this node has no any node which is not visited, so it will trace back, trace back, trace back. Now it will come here and visit this node. It will visit this node. Now there is no any node with unvisited from this node, so it will trace back, trace back. Now the DFS function is over and return to main. Okay, so this is how it works, the DFS function. Here you have to observe one thing, that this node is, this edge is unvisited, this edge is unvisited, this edge, not the vertices, this edge is unvisited and this edge is also unvisited. So these four edges are unvisited. What does it mean? Actually these are called the back edges. Okay, these are called the back edges which are not visited because it was already visited. That's why you did not traverse that edge. This is called the back edge. Now one observation is that a back edge cannot be the bridge. Back edge cannot be the bridge. Back edge can't be bridge. You can think upon that. Why it cannot be the bridge? Because since it is already connected to the parent and this is connected to the ancestor, this bridge, this edge is connected to its ancestor. So even if you remove this edge, it will still be connected. This vertices still be connected from the parent. So the back edge can't be the bridge. Okay, this is the DFS tree, and the observation that back edge cannot be the bridge. These are the two things that we learned. Now how we are going to find the bridges? For that we have to carry on two vectors in which we will be storing the in time and the load time of the any vertices. What the in time and the load is. So what the in time is, I am writing what the in time is. In time is the time at which that node is visited. Time at which that node visited. And what the load time is? Load time is minimum ancestor from which that vertices is connected, directly or indirectly. Minimum in time vertice minimum in time vertices having the minimum in time is connected directly or indirectly. Directly or indirectly. Okay, So directly or indirectly, how it is connected. How we will store the end time? So in the DFS call, when we traverse any node, there can be two types of nodes that we will be traverse. There will be three type of nodes that we may traverse any nodes. So suppose if the traverse here, see here, if this node is there, if this node is there and it started traversing its child, then there may be the cases when its child is not yet visited. The second case can be the child is visited already, and the third case may be it is its parent, which is this in this age. In this case, maybe its parent. So these are the three cases when any node is traversed to its child. So these are the three cases. What we have to do in these three cases, we will see here. If the traverse node, this we are traversing the child of any current node, if this is a parent, then we will do nothing. If this is a parent, then we will do nothing. Else, maybe it children is already visited, then that will be the case of backage. In that case, we will update the load time of the node. By load time of the node is minimum of load time of the node and end time of the child that we are trying to traverse, but we are not traversing because it is already visited. And this is the third case. This is the third case. So this was the first case, this was the second case, and this is the third case. If it is not visited, then we are calling a DFS call from here, and after that we are checking it if the edge that we have traversed is a bridge or not. And this is the condition for any bridge, that the load time of the child is greater than the end time of the node, then that edge will be the bridge. I will explain in the example above. Wait, just see this now. If it is that, then this is a bridge, and we will update that current node also. We will update that current node also. Okay, by minimum of load time of the node and load time of the child. So I am going to explain this example in the next video. So just this was the overview of how we can find the bridges. In the next video, I will be explaining this example together with the code in a good way, in a detailed way. Okay, thank you very much.